This lecture covers why we would choose to use a pooling layer when we are setting up a convolutional neural network. Far, we spent a lot of time talking about convolutional layers. They're harder to understand and trickier to grasp. Pooling layers, on the other hand, are much easier to understand. The whole idea of pooling layers is to allow you to subsample the inputs. The goal of the pooling layer is to shrink the input image in order to reduce the computational load on the neural network, the memory usage for training, and the number of parameters. Pooling also limits the risk of overfitting the training dataset. The neurons which make up a pooling layer have no weights or biases, so they don't apply any kind of multiplicative effect on the input. A pooling neuron simply aggregates the input in some way. The pooling layer essentially is an aggregation function such as max, sum, average, etc. In addition to shrinking information that is passed into the input, if you just extract and aggregate, you're essentially shrinking the size of the input. This also serves as an abstraction, extract the most essential features from the input. We'll see how pooling works by taking an example of how a max pooling layer works on an input matrix. Again, we'll consider a fairly simple input matrix. This is a 4 by 4 matrix. Just like in the case of convolution, pooling also uses filters. However, these are max filters, sum filters, or some kind of aggregate filters. Here we are going to apply a 2 by 2 filter with a stride of 2 in the horizontal as well as the vertical direction to get a pooling result which looks like what you see on the right side of your screen. This 4 by 4 input matrix on the left will be shrunk to a 2 by 2 pooling result. This pooling filter will start off with the top left corner, just like in the case of a convolution kernel. This filter, when applied to the four values that are highlighted, will choose the maximum of these four values to write to the pooling result. The filter applies no weights or biases. There are no multiplicative factor. The maximum of the values here is zero point 0.9, and that's what is written to the pooling result. The pooling filter has a stride of 2 in the horizontal as well as the vertical direction. So move the filter over to the right by 2 columns and then apply the maximum aggregation once again. The maximum of the values here is zero point 0.8, and that is what is written to the pooling result. Move the filter down now. Since we have reached the edge of our input matrix, the filter will move 2 rows down because its stride is 2 in the vertical direction as well. The maximum here is zero point 0.8, and that's what is written in the pooling result. And the last max pooling filter result is zero point 0.9. The sliding window for pooling is now complete. If you remember our discussion between convolutional neural networks to work on images and dense neural networks, you might remember that dense neural networks had several drawbacks. One of the most important drawbacks were the number of parameters that would need to be trained if you used dense neural networks on images was simply huge. Convolutional neural networks are sparsely connected networks, and it greatly reduces the number of weights and biases that have to be trained. And this is where pooling layers really help. Even sparsely connected convolutional neural networks might take a long time and use up a lot of memory during the training process. The addition of pooling layers, which shrink the inputs, greatly reduce memory usage during training. Pooling layers help extract the most important features from the input matrix, and this greatly mitigates overfitting. We've spoken about a core problem when we use neural networks on training data. Neural networks are high variance machine learning models, which means they tend to overfit on the training data set and perform poorly when you work with real world data. Pooling layers, by extracting only the essential features of the input, allow us to mitigate overfitting. Pooling layers, in addition to convolutional layers, allow us to introduce location invariance to feature detection. These allow neural networks to recognize features independent of location. The features are represented by their most essential characteristics using pooling subsampling, which is why these features will be recognized no matter where they exist in the input image. Typically, when we use pooling applies to each channel of the input image independently. So if you have a color image with three channels for RGB values, Pooling will apply to each of these channels independently. The pooling result will have three matrices, one for R, G, and B values. The same applies to feature maps as well. If the input feature map has a depth of 32, that is, the convolutional layer to which pooling is applied has 32 feature maps, then the pooling result will also have a depth of 32. So the effect of pooling is that the area of the input is shrunk. Output area will be less than the input area, but output depth will be equal to the input depth. Pooling layers subsample the input matrix by applying an aggregation function such as sum, max, average, etc. Pooling layers reduce the dimension of the input matrix substantially, which is why they greatly reduce memory usage during the training of your neural network. Pooling layers also mitigate overfitting via their subsampling. Pooling layers also make your convolutional neural network location invariant. That means features that are detected in one part of the image will be detected had they existed in another part of the image.